Welcome to my presentation. I always like to start to thank all the different collaborators, and I think there are probably also some missing of that. So thanks a lot for all the great years here, and yeah, they all contributed to that work, which I'm going to show you. So the main challenge which I think exists currently with respect to time-dependent PDE solvers is how to accelerate them if they are at a limit of scalability. And there's one particular application which I love to work on. It's weather simulations. Because they play a very important role in our daily life, and they have very hard constraints with respect to time to solution. So they have to be finished within an 1 hour time frame window on the supercomputers by the operational centers. So it's a very particular challenge to run them. And I'd like to give you a little bit overview of what happened in the past and about my 3 heroes. And so this slide is about my first 2 heroes. And the first one is Louis Fry Richardson. And I think you never heard about him, but he was really the first visionary person to think about that actually numerical forecasts, weather forecasts can be done. But this was at a time when no computers have been invented. And so he referred to computers as someone who computes. And the underlying idea is that he discretized your sphere, your Earth here. And he thought about building such a dome here and then putting human computers here on these galleries. And then they can signal the results to these operators. And then he also developed his first discretization itself, but it turned out later on that the discretization itself was unstable. But at least he was the first visionary to think about running these weather forecasting systems in a numerical way. Then the second one is some guy who you definitely know about, at least you should know about if you are from computer science. It's John von Neumann, the genius in all different kinds of areas, let it be mathematics for the von Neumann stability analysis, for instance, or you also know him from the von Neumann architectures, so the architectures underlying also our current, at least CPU-based systems. And he was the first one, so well, he did many things, and he also ran one of the first, which I would call weather forecasts on a computer. And this was the ENIAC computer itself, and this was a simplified model, and I'm also using these simplified models to study time integration. In this case, it was a single-layer vorticity equation. So at this time, everything beyond that was computationally too expensive. And so they simplified everything down to this equation. And that's really what I consider to be the first weather forecasting system. Yeah, and maybe this ENIAC, which was hardwired, that inspired him even more to develop with his colleagues the ideas around the von Neumann architecture. So if you think about weather simulations, we need to first think about the discretization of the atmosphere of the Earth. And in order to understand the different scales of that, we know that the circumference here is given by around about 40K kilometers. And then if you think about the different, so that's the horizontal scale. And then if you think about the vertical scale, and the distance here is a little bit exaggerated. So it's really a very thin shell on which we are working on, and what our atmosphere is actually about. So people say sometimes that the atmosphere ends here, which is relevant here at 100 kilometers. Sometimes we can have deep atmosphere models with more, sometimes less. So yeah, but it's of this order of 100 kilometers. To give you some impression about concrete resolutions, and if you take the ECMWF, that's the European Center for Medium Range Weather Forecasts, and if you take the resolution here from the previous year, they had a 9-kilometer resolution here in the horizontal itself, so around the Earth. And then for the vertical itself, they have around about 130 cells. And these cells are then scaled with 20 meters down on the ground. So it's just 20 meters cell size itself, if you're close to the ground, and up to 6 kilometers in the upper atmosphere here. So you see that we have to cover these different scales as well in these simulations. And then, well, the consequence of that is that if you develop new numerical methods, let it be in space or time, you first study that independently to each other. So you say either you first analyze that and develop these methods for the horizontal parts, or you do the same things here for the vertical parts. So pick one. And for the vertical parts, it's very common to use 1-dimensional or 2-dimensional slice models, and then you investigate these different things, different grid layouts, how to include topography, for instance, or also time integration methods. And then if you think about the horizontal aspects, you simplify that to a 2-dimensional problem, which is either existing on the plane or, as I will do that here, exists on the sphere. So it's just a thin layer on the sphere, which I'm using as a proxy model for these for the fluid dynamics equations approximating the atmosphere. And again, then there are different ways. If you would do more numerics in space, and we would study these discretization in space, mimetic properties about physical preservation, for instance, or what my specialty here is on time integration methods. So how do we get from these three-dimensional Euler equations down to two-dimensional equations? And let me first introduce you to the equations here, which I'm going to use. So we start here for the simplification with these equations here. We have that in Lagrangian form. So this is following the trajectory here of that. And rho itself refers to the density. V would be our two-dimensional, in this case, three-dimensional velocity component. Then we have this term here. This is now the term which is incorporating the effects of the rotating frame, because we are rotating around the Earth here. And basically what this term is doing is that every time if you move into a certain direction, in the horizontal direction, you're getting pushed away in a direction perpendicular to you. And the faster you move, the stronger this pushing in the perpendicular direction acts here. So this is basically this term here. And then you get the other terms, which we're going to simplify a little bit. So because we are interested mainly in numerical effects, in the time integration effects, we can further simplify them. And we can apply the hydrostatic balance here, constant density, depth integration. And then we end up with equations which can be now related to the Scheller-Watt equations. And I'm pretty sure that a lot of you are familiar to the Scheller-Watt equations. So we can then rescale certain parameters of that. For instance, this one here, it's the shear potential. It's given by the gravitational, so by g times, and then the height of the Scheller-Watt surface itself. And here we have again our rotational effect from the Coriolis effect. So we have the most important terms included. Also this term here, so this is the gradient of the shear potential itself. And the advection part is hidden here in that Lagrangian form here. So this is a form which is following these trajectories. And this is a very common equation which is used to study all these spatial and temporal discretizations. So if you show that a numerical method doesn't work for these simplified equations, it will never work for these equations. And once you get it running here for these horizontal equations, it's actually straightforward to extend that to the 3D equations once you solve also the vertical. But my talk is mainly focusing on the horizontal aspects using these Scheller-Watt equations here. Okay, now I'm going back again a couple of years, almost 50 years, to my third hero. And my third hero himself is André Robert. He was the leader of the numerical group of Meteo Canada, the Meteorological Service in Canada. And what I'm going to explain is not how you find it in his papers, but it's how I'm explaining you that simply with Scheller-Watt equations, because it simplifies a lot of things here. So instead of now treating a PDE, partial differential equation, as it is, just saying, okay, these are the terms, and we just apply whatever off-the-shelf time integrator, the underlying idea is that we break it down into different components. And the different components here are given, first of all, by this linear gravity, so it's called fast gravity mode terms. It's related to gravity modes, which are here in this form here. And this overbar here denotes the shear potential, which is now a linearized state, so the average state of the shear potential, and we refer to the variable itself is then the perturbation on top of that average state here. So you have a linearization in that, and then we get this purely linear term. And what this term is doing is basically creating very fast oscillations. You can think about that to be acoustic modes. If I'm clapping into my hand, there would modes propagate or waves propagating here around, and that's basically included here by this term. And so the first step, what has been applied at this time, so it was around this time here, it's to treat that term implicitly, because it's the most stiffest term. So that's the term which is limiting your time step size mostly, and the other terms are not that restrictive. And if you treat that implicitly, then you get directly a time step size increase of 7 to 10. And well, André Robert was the first one who did that with spherical harmonics. So this method has been developed before. If you use spherical harmonics, you know that you can solve this particular term here. You can reformulate that to a Laplace operator and then solve it directly in spherical harmonic space and get also a significant speed up also of 7 to 10. So this directly relates to that. Okay, this Coriolis effect is not included here. That's the Coriolis effect, which is again taken into account the rotation of the Earth. And it's a very, very small effect here. So with respect to time step size, it's not really limiting your time step size, at least not compared to this nonlinear advection term here. And then, so this is what André Robert and others also did as a next step. So there have been a lot of steps in between of analyzing methods around that. And here the idea is to take, again, the Lagrangian perspective. So taking the total material derivative here on the left side and treating that term here in a Lagrangian way. And a lot of papers have been developed around that. And André Robert was then the first one who put that also into an operational code against spherical harmonic space. Now, if you take that Lagrangian treatment here, you eliminate this term here. And then again, you get a stable time step size increase of a factor of 4 to 6. And you might think that, well, It's nice. And how about the real speedups? And well, regarding the Wolfram time reductions, the speedups, you only gain a factor of 2. And it doesn't sound really impressive, but if you think about weather forecasting systems, a factor of 2 means that it can also increase your resolution, not really by a factor of 2, because that leads to other effects again and reductions of the time step size, but you can at least slightly increase your resolution by having the same computational workload then. And so this was, again, a huge impact here. And nowadays, most of the cutting edge weather forecasting systems are based on this Lagrangian treatment. And then we have this nonlinear remainder term here. This is a term which is often treated explicitly. Okay, yeah, and as I said, they're used operationally by the European Weather Service, for instance, by the Met Office in the UK, or also by Meteorforce. The next slide is about explaining what the semi here means. So the semi-Lagrangian methods, because if you would have only a Lagrangian method, it's a particle-based method, it doesn't really improve the situation a lot regarding the computational complexity. So now you see that we take the total material derivative here, and if you would just take a Lagrangian method, we would have particles, and then we would have a lot of particles, and these differential operators would need to be evaluated across all these particles, which is something which we don't want to do because it's computationally very intensive. So for computer games, it's nice because we can take a lot of approximations for that, but for PDEs and for operational simulations here, it's simply too expensive to take that approach. And there are other issues showing up, such as conservation of momentum, conservation of energy, for instance, which is not that easy to solve here. So what can be done is to take a semi-Lagrangian perspective. And the semi-Lagrangian perspective is a mix between a Lagrangian view and an Eulerian view. So with a Lagrangian view, we follow these trajectories here, but in order to evaluate these differential operators, we take the Eulerian view so that we go to the grid itself. So, and instead of just following these trajectories and then saying we interpolate at some point, we interpolate these values here back to the grid, we go the other way around because we always want to ensure that these points where we need to evaluate that can be interpolated with the surrounding grid points here. So what we do is to start at the arrival point, because we know that this is where we want to have the values to evaluate these PDEs itself, and then we go backwards in time, and then we know that if we go again to the grid itself, we can interpolate this value here. So this is the Eulerian view. Then we can interpolate this point again from these grid points here and get a good approximation for that point here. So that's the semi-Lagrangian method as it's nowadays used operationally. And yeah, the particular implementation is a little bit more complicated. I just want to refer to the ZTLS scheme, and this is also what I'm going to use in this presentation here. And it's a scheme which is used since many, many years by the European Weather Service as well. Okay, now that leads me now to the first time integration method, namely about exponential integrations. And that's a joint work also with Richard Loft and Nathaniel Schreiber. And I'd first like to give you a short introduction to exponential integration methods, since I think it's not every one of you might be familiar to that. And we're focusing here first of all on linear PDEs. And we know that we can write these linear PDEs, so we have the time tendencies of u is equal to the linear operator applied to the current state. And if you apply some mathematics here, we can write that as a solution of the next time step here, t plus delta t is equal to the exponential of delta t times L, and then apply to our current state. And if you're not familiar to this exponential of some metrics here, it's no problem. I will explain that step by step, but it's very expensive to do that operator here. So it's computing the exact solution here, the exact solution with no errors in time. This is basically what this expresses here. And if you take that formulation here, you don't have any time step restrictions anymore, as long as you have linear PDE here. So you can take arbitrary long time steps with this form. But again, the question is, how can we approximate that efficiently? And there have been different forms developed over the last couple of years, Krylov-based methods, polynomial approximations. But my specialty is to work on these rational approximations of exponential integrators. And I'm always using the abbreviation REXI for this rather complicated term here. So we want to find an efficient approximation for that exponential of delta t times the linear operator. And the method I'm using here is this rational approximation where we have this beta here. You can imagine that as a denominator here. I will explain that further here. And then we have, again, delta t times L minus, and then identity matrix times these alpha poles here. And that's how we try to approximate this exponential. Before explaining you how we infer these alpha and beta coefficients themselves, I just want to provide a brief motivation why we like to do that. And this idea has been born already over 20 years ago. So you find these ideas also in papers of mathematicians who applied that. And so in order to approximate again our solution at the next time step, we take this rational approximation. And now we can think about computing that sum in parallel. So you take your current state U, you broadcast that to all these different REXI. You can broadcast that to a full supercomputer if you like, and then you solve for these linear systems independently to each other. So it's a linear solver which you need to apply here. Then you just scale it with this complex valued beta coefficient here. So these are the solver parts, totally independent. And then you apply the reduce operation here. And then you have your result here at, again, these ranks. And now it sounds quite tempting to try that on your own, but let me just put out some warning here. I'm using a trick here, which is in spherical harmonic space. So I'm always getting not a perfect diagonal system, sometimes a diagonal system, but a banded diagonal system here. And this allows me to solve these so-called Helmholtz problems, which I would get then in the end highly efficiently. And if you think, oh, we can solve Helmholtz problems, then you know about the good Helmholtz problems, but the original Helmholtz problems can be relative wave propagations, and there's no efficient solver so far developed on Earth to solve them efficiently. And this is what you're facing for certain alpha coefficients. So sorry for taking away a lot of excitement in advance, but this is one of the big challenges to develop efficient solvers for that. But well, I'm using spherical harmonics to solve them here. Okay, so how can we find these alpha and beta coefficients? And so instead of taking this like standard time integration perspective where you approximate tendencies, the only thing you need to do here is to think in terms of ODEs, where we can write that as this, and then we know that we can find a direct solution for that directly by that. So we have the exponential of delta t times lambda itself here, and then again our current state of that, and this is our future solution. It's just written that down directly. If you now think about how that exponential looks like for lambda itself, so we know that for purely oscillatory problems, so for wave propagation problems in particular, we only get imaginary values here. So imaginary values. And also for our linear operator itself, the linear operator here, we have only purely imaginary eigenvalues. So we can relate the linear operator again to a spectrum of these lambda coefficients here. And what we need to approximate is in the end this landscape here. So this is the real part of the exponential. This is the imaginary part of the exponential. That's here, it's a complex plane, the coordinates on the complex plane. And then what we need to do is to take this linear combination of these basis functions, you can see that as a rational basis function, and approximate this exponential here in the region here where we want to evaluate that. So depending on the time step size, you need a larger region maybe, or if you take a smaller time step size, a smaller region here. So that's everything which we need to do here with this rational approximation to approximate the landscape. And then if you have a PDE solver, again, we can think about these lambda coefficients to be given by the spectrum of the linear operator itself, and that's again exactly the range where we need to approximate this exponential landscape here. And in this way, we can infer our alpha and beta coefficients, and we're going to explain you at least 3 different methods here how we can infer these coefficients. Okay, and the first method is the most beautiful method I ever ran into for time integration at least. So whoever thought about that we can time integrate with Cauchy-Contour integration methods? It's more a theoretical construct where we say that if you have a function itself and a function f itself, and you want to evaluate that function at one particular point, and this point could be one of these lambda coefficients here. So it's a spectrum here. This should symbolize the spectrum of the linear operator on the complex plane. And then we want to approximate this function here. This is our exponential function here on these arbitrary points. And instead of evaluating that directly here, we can instead take the contour of that around these points where we want to evaluate them, and evaluate the function instead on that contour. So we evaluate that instead of this contour here. This is where we evaluate this exponential function itself. And then we can apply a trick, namely, we can use an a priori computation of that with the trapezoidal rule. So we discretize that contour here with a trapezoidal rule, and then we get this contour here, it's a circle contour in this case, and then we can again infer these alpha and beta coefficients and get our rational approximation again of our exponential function. So this is how we can use the Cauchy-Contour integration method to approximate the exponential itself. And then we can use that again in our time stepper to write our exponential of delta t times the linear operator using the very same coefficients here as we inferred with the Cauchy-Contour integration method in here, and then use that again for our time integration scheme. Okay, then in order to assess that, what we can do with that, I'm taking this barotropic instability benchmark. So it's one of these standard benchmarks which we use in our community of dynamical core developers to assess new time integration methods or numerical schemes in space and also time. And so I used a reference solution here after 122 hours, and I used the fourth order Runge-Kutta method here because I'm comparing that to second order accurate exponential integration methods. And here you see how this simulation looks like. So you have this a jet stream here. It's stable at the beginning, and then it creates these characteristic vortices here, and then I'm stopping the simulation and I'm comparing my results to that. Now let me guide you briefly to that plot here. So the x-axis itself shows the wall clock time, and what we want to accomplish is to have less wall clock time. So to go to the left side here in order to get our results faster. And then the y-axis itself, x-axis itself shows the error on the surface height itself of these shallow water equations, which can be also related, for instance, to the density of our weather simulations. And then we see that the three best methods here which we use are based on a strength split REXI method. So this includes nonlinearities, and included the nonlinearities here with a strength splitting approach here. And then we see also that the best other method here, alternative method, which exists here, is the strength split Crane-Nicholson method, which you can see here. And we observe that all these REXI-based methods, all these rational approximations always outperform these standard implicit methods. So it's an explicit implicit method implemented here. We also see that there are some sophisticated exponential time integration schemes here. This is exponential time differentiation, second order Runge-Kutta scheme developed by Cox and Matthews. And we see that if you take these schemes here, they are claimed to be really outstanding. It's computationally pretty bad for these problems here. It's because they haven't been really tailored to that, and they require a lot of additional exponential integration evaluations here. So basically a lot of REXI evaluations here, which makes it computationally quite expensive here. So the takeaway message here is just take the straightforward strength split REXI method here, and then you see that we get either 3 times faster or we get a 6 times reduction of the errors itself. Should also emphasize here that we used 128 poles here. So if we apply this method, even if you get better results, you need to be aware that we pay the price of using 128 additional computing resources. So this is simply what you have to invest if you choose that method here. Okay, now let's continue to 2 other methods here. I don't show you results about that method, but I at least want to show this method, which I'm calling the T-REX method. It was developed by Terry Hort and others. And here the underlying idea is, again, just approximating that exponential itself. And so here the thing is that you first take the real parts and you take a linear combination of Gaussian basis functions to approximate these oscillations in a certain range here. That, again, depends on the spectrum of your linear operator. Then we take a linear combination of rational functions, again, to approximate the Gaussian itself. And then we can take this approximation of the Gaussian, insert this linear combination itself, and then, again, combine this real parts, the real approximation of our exponential function and the imaginary approximation of our imaginary approximation of our exponential function, and combine it together, and again enter that REXI scheme here. So this is again how you get another REXI scheme with other alpha and beta coefficients, but this only works for pure oscillatory functions here. So it's developed specifically for these oscillating problems here. And the nice result here is, I'm not going to show you that we can compute arbitrarily long time steps here. So with time steps which were limited by 60 seconds, and we were able to take time step sizes of 1.5 days. So gigantic large time steps only using a linear PDE in this case. Okay, something which you might be more familiar with is the butcher table formulation here. And we can take the butcher table here, for instance, which is this A table here, and we can apply diagonalization of that. So it's a standard trick here. And this trick itself has been developed by Butcher and Bickard almost 50 years ago. So there will be soon a 50-year anniversary for that. And if you take that and if you apply certain other reformulations themselves, we again can write that in terms of this REXI form. So we get this gamma coefficient. It's an additional coefficient which shows up for certain quadrature rules here. So it's a collocation method, and depending on which quadrature poles you use, this gamma pole shows up or not. But in this way, we now have a really unified REXI formulation here, which allows us to express whatever REXI methods we have in this unified form. And again, you see that it boils into this beta coefficient alpha, and again, this one here, and we have to solve for these systems. So it allows you now to replace this fully implicit Runge-Kutta method, which would have a dense table, which would be very expensive, to independent backward order steps here. So you can interpret that as a backward order step, but you need to cope with a complex valued shift here on the diagonal itself of that linear operator. But it inherits all these beneficial properties of the implicit Runge-Kutta method, so perfect stability and amplitude preservation on the imaginary axis. But it also gets unstable if you use more than 16 poles for that. So if you have more than 16 stages here, it simply breaks down because of ill-conditioned decomposition here, which we are using. But well, we can at least try to apply that for less poles. And that's exactly what I want to show here on the next slide. But here, this slide first solves some fairy tales because people always claim that exponential integration methods are so great. And now what I'm showing you here is just a direct exponential integration based on the linear terms here, because we can directly exponentially integrate them without any rational approximations. So what you see here is the result of a strength splitting method here. It outperforms definitely this best ETD-RK method here, which you see as these blue dots. I'm just showing time step size versus error comparisons here. So these are not yet void time comparisons here, but we can make very, very clear thoughts here around that. If I'm taking an implicit method here, an explicit-implicit split method here, these are the green lines here. You see that, well, they don't perform really well. And then what's in the background here and the gray lines is that we observe that we have these different first order forward Euler method, second order Euler method, fourth order, a second order Runge-Kutta method, fourth order Runge-Kutta method, and you see that these Runge-Kutta methods, high order Runge-Kutta methods, simply outperform whatever exponential integration we try to apply here, which is a pretty nice result. Except of this point here, where we see that we can take gigantically large time steps if you take this strength splitting method and the Runge-Kutta 4 method here, this stops having stability here. So it's in the background here. Sorry for that plot. Now, if you think about REXI approximations, rational approximations, how they perform, we can now see that, for instance, for the Butcher tableau-based REXI methods, we observe that, so it's the green ones here, the green lines, that if you take just one pole here of the B-REXI methods, just basically a one-stage method which we apply here, we observe that this would lead to these results here, and we observe that this matches exactly a strength split Crane-Nicholson method. So if you time integrate the linear parts with a second order accurate Crane-Nicholson method, and in fact, if you use that REXI method with just one pole, it directly resembles the Crane-Nicholson method. So this is why these results are matching here. We see another interesting effect that if you have just two poles of the B-REXI method itself, we get these results here. That's the left pointing triangles here. And if we have a look at increasing number of poles, like using 4 poles here, 4 stages here of that Butcher table itself, we see that this doesn't lead to any improvements. And we can now also see that if you use a Cauchy-Konto integration method with 128 poles, this still doesn't improve anything. And now the main takeaway message here is that we only need actually 2 poles here, 2 poles in that approximation using this Butcher table diagonalization technique. And it's competitive to our previous Cauchy-Konto integration method, which has been considered to be the best method so far, which took 128 poles. So now we can have really competitive results with just 2 poles. And that's a considerable saving with respect to the compute time. Well, all these things don't matter if you don't make wall clock time studies. So this is now what this slide shows here, where we observe that this still the Runge-Kutta methods, 4th order Runge-Kutta methods are performing best. But we know that higher order methods always perform better. But we now observe this scheme here, that again, the B-REXI methods here are the best methods here of all the different REXI methods. And if you think about these B-REXI methods with just 2 stages themselves to be related to a 4th order accurate implicit Runge-Kutta method, it also tells us one thing, namely that we can actually replace this computationally very expensive exponential integration itself with maybe just a 4th order accurate implicit Runge-Kutta time integrator. So it's a good alternative to all the previous schemes which have been developed here, just to replace it with this 4th order implicit Runge-Kutta method. Yeah, just some further comments on that. So these are just some results which are now computed based on the geopotential itself, comparisons on the geopotential, and they can change a lot if you take vorticity into account, for instance, or some other physical properties. So please don't take them as granted that this is now the full answer to everything. Definitely not. So we need to study by far more physical properties here. Okay, then I open up my second part here about parallel spectrally inferred correction methods. And to make sure that every one of you understands these methods, I'd like to just give you a brief introduction to the Picard form and how we can actually infer these collocation methods. So we know that we can write an ODE as solutions of the ODE for the starting point as the integral over my time tendencies here on the right-hand side. And then the standard trick is to use a quadrature points across across all these integral points here, and then approximate again the solution at a certain point of that quadrature point here by tau m, so at the point tau m itself, and then we can write that again as this quadrature, where the quadrature weights again are given here by qmj. This is also what we used in the previous case to infer our Butcher table itself. And then we can write it more compactly in this form here. So we write this u at the different points, the quadrature points, as a vector here. And then we again get this linear form here where q, all these weights are stored compactly in this Q matrix itself. And then we can take another reformulation of that, which says that we can take an iterative form. And the iterative form is then given by that. So in order to find the next update, we can take our current solution and then we evaluate this term here. So it's basically just adding UK on the right side and saying the left-hand side is then given by UK plus 1. Okay, so this is now what we can use. And if you use a higher order quadrature method here in this Q matrix to infer these coefficients here, we also get a higher order method basically for free, just with this fixed point iteration. Now, let me talk about spectrally inferred corrections. And if you're familiar to them, I will take a slightly different perspective to infer them. So you can write the spectrally inferred correction methods again based on this Picard form. So what you showed before as Q form, and you can interpret the spectrally inferred correction method then simply by applying this matrix here in this way and applying arbitrary integrators which integrate that from one sub-time step quadrature point to the next point here. And so the update itself is then given by that you have your current your state at u0 here, that would be at the beginning, and then you apply this time integrator, whatever time integrator you like to use in that. Based on UK itself, this was from the previous iteration here, and then you apply again the time integrator, whatever time integrator you want to apply to on the current state itself. And this could be, for instance, an IMAX method, implicit, explicit, split method, whatever you prefer. And this is how we can write our spectrally inferred correction method. So how that works, if you implement that, is basically you start here at this one point here, and then you apply this whatever time integration method you want to apply here. So this I here could be an IMAX methods, implicit, explicit, exponential, whatever you want to do. Then you just time integrate that with a very low order. And then you can apply this iterative scheme here. And then in each additional iteration here, by applying this equation here, you get an additional order of accuracy here, up to the quadrature order of your method here. And this is simply what we like to use here and what we want to investigate. And these are then the different variants which we can use. The main challenge of these STC methods are that they are still sequential over the nodes and the iterations themselves. We need to go step by step over these nodes and step by step over these different K iterations. And now one remedy of that is to think about using a preconditioner of that. Again, it's similar to what we did before, to find some better approximations of that instead of just using the fixed point iteration. And if you use a preconditioner here, we can find a preconditioner like that. And then we can apply the preconditioner, reformulate it like that, and then choose that Q delta matrix here in a way that it's diagonal only. So this is the main trick in here, to think about the Picard formula or STC iterations as a precondition iterations, that we can use a preconditioner which is diagonal only, and then solve for all these terms here independently to each other. And then we get to this parallel STC method here. So this is a method which has been suggested by Robert Speck a few years ago. Now we can apply that again. I'm skipping a lot of details. This is just submitted work here, so you're the first one who see that now in a public audience. So in order to apply this parallel STC method, we did some performance comparisons on a shared memory parallelization with 4 numodomains, and we use up to 4 stages across which we can parallelize. So this is where we apply our diagonal preconditioner on. And then we compare these IMAX methods versus these parallel STC methods here, and we see then these results. So that's wall clock time, less means here going to the left side, and the errors here on the y-axis here, lower means, and we have less errors here. And you see that if you apply these parallel STC methods here, they definitely outperform the standard IMAX methods, second order IMAX methods here in this region here. But then we also see this nice crossover point up here. And this is really something which I like to emphasize a lot, because we see that suddenly this IMAX method is getting the best method for this particular point here. And this is exactly the region where we are interested in running weather and climate simulations, because taking less wall clock time means we take the largest possible time step. And so for this case here, we would actually choose the IMAX method, whereas for these points here, if we really want to reduce it even further, we would choose this parallel STC method. And again, this is just one of many plots which we then can provide hopefully soon in this publication here. Okay, then the next method I'd like to briefly talk about is the parallel full approximation scheme in space and time. And it's briefly explained as follows, namely that we have three basic ingredients to that. And the first ingredient is the spectrally third correction method. And the spectrally third correction method is required here because we need a higher order method in order to get certain convergence if we apply a parallel in time method here, which is called Parareal method. So we need accurate phases in here to get a convergence. The second ingredient of that method is to use a multi-level in space method. So in this case, we don't always want to work on the highest resolution, but go to a lower resolution, because if you take a lower resolution of that, we can take larger time step sizes. So otherwise, we would need to take these small time step sizes. And the cost of the resolution is the larger the time step sizes are, which we can take. And now you have to imagine this multi-level scheme here, as these are the quadrature nodes here, and all this entire scheme is applied with a spectrally third correction method here. And then as a third ingredient, it's about a parallel in time method, where you say you have your initial condition here, and then you compute very rough approximations parallel in time here. So you say this is the Wall clock time itself. This can be very quickly computed, so not too much Wall clock time here, but you can advance quite well in the simulation time. But the results are not yet that accurate. So this is denoted here by this blurry picture here. I hope this is a good depiction of that. So it's just an initial guess for that. And what we can do next is to say, okay, given these good approximations, we take again a fine time stepper. So this is our regular time stepper, which is very expensive. So that's why we have a long distance here in the Wall clock time dimension here. And then we advance it further here. And that this can be done again parallel across all these different coarse approximations here. And after that, we apply correction schemes. So it's an error correction scheme, or you can imagine that as an error correction scheme across the time dimensions. We correct them, and then hopefully we find some convergence in the end to provide the best results. And then we continue doing these things. And very often we use like 16 or 32 instances here in this across the simulation times, chopping that into 16 or 32 additional computing resources, and then applying that iterative scheme across 16 or 32 additional computing resources. Okay, so that's just yet another animation around that. So you have our coarse time step. This is a fine time stepper. This is computation time here. And then we need to communicate these things to the next processors here. And then if we get some convergence, we should be able to finish much earlier than running this stuff here sequentially. Okay, so now how does it look like? So we published two papers about that. One just using the regular multi-level spectrally third correction method. But for sake of time, I just want to show you that overall result, which is taking all these three ingredients into account. And here we see that, again, results with a barotropic instability benchmark, so the same benchmark as we used before. And we observe that using the SDC method, so higher order methods, this would be our Wall clock time here on the x-axis, and normalized L infinity error here on the y-axis here. So lower means better here, also going to the left, so getting the results much faster. And we observe that for the SDC method here, and for this SDC method, that whatever we do with this parallel in time method with FAST, we are better than these standard SDC methods. So in the end, FAST is in this case Pareto optimal. And I should also point out that this is on logarithmic scale. So the speedup is quite significant, which we get here. Well, I should also emphasize that we had to add some viscosity here. It's a common phenomena that for parallel in time methods, if you have a hyperbolic problem, so purely wave propagation problem, you have to add viscosity for sake of stabilization. And it's one of the main issues here, which we had here. And we also worked on that, but in a slightly different context. And this is the last part of my presentation. It's about using also a slightly different algorithm here, MultiGrid in time, to solve certain other issues. So first of all, the problem with FAST is that we always applied a fully higher order method for the full PDE. But we know that actually we only need to resolve the fast modes with a higher order method to track all these frequencies in that. And we can treat the lower frequency modes actually with a lower order method. So we should need, or we want to have more flexibility than just using a higher order method for all these terms. And the second issue is that we need viscosity in order to get stability. So it simply blew up, and yeah. So for the first, the remedy for the first solution is simply to switch to MGRIT, and MGRIT is an algorithm which has been developed by people in the States, and so it allows us to move away from these higher order methods, and we can now just apply whatever methods we want to apply. And in this case, on the fine grid, we use an IMEX method, so implicit explicit split method, And on the coarse grid, we are using an IMIX method, and I should emphasize it's not necessarily coarse. On the same resolution as a fine grid, we can also apply a Semi-Lagrangian scheme. In this case, it's a set-TLS scheme. So we don't lose any modal information here by going from that grid here to this grid here, because we use the same resolution also for these Lagrangian methods. So, but well, the issue about viscosity is still left. And if you know about, or if you work in this area of climate weather simulations, you always run over these kinetic energy spectrum plots. And so it's what Kolmogorov did a long time ago, that he said and predicted that the kinetic energy spectrum for very long running simulations has to behave like that. And then what we get, because of numerical issues, is to have some uptailing or downtailing here, the limit of the spectrum here. So K itself refers to the particular mode which we have here. And we know that there's always an error here at the limit of the resolution. This is caused by a lack of nonlinear interactions, because it can't interact with modes which are not resolved here. So we get significant errors in that. And now think about a multi-level method. If you have a multi-level method, we have this truncated solution here, and we also get this uptailing here. So sorry for these catches here, but this is just how I imagine how these things look like. And what we see here is that, well, you always introduce some additional errors here if you do the coarse solution here to the final grid. Even if you take a full approximation scheme, it's introduced here as long as no convergence is reached. So the full approximation scheme which is used here only ensures that you don't introduce errors once you really reach the accurate solution, but not in other cases here. So as long as we are not at the accurate solution on the high resolution itself, we always inject certain errors here. But now the idea is that we can apply a certain filtering method here in order to get rid of these modes which are some troublesome. And this is where we apply our hyperviscosity filter here only on the lower resolution, only on the lower resolutions here. And so this is now some benchmark where we just started different Gaussian bumps propagating around that. We are comparing that with a set-TLS scheme with 3 multi-layer levels, multi-levels here. And we add this hyperviscosity. And so this is now a plot which shows you the different viscosity which we had to the different levels here. That's on the level 1. So there's also level 0, which has no viscosity at all, because we want to converge it to the solution without any viscosity. And this is our next level here. And this depicts the different viscosity here. And this Q equal to 2 means we have a regular viscosity. This is a hyperviscosity, and this is an even higher order viscosity here. And then you see that if you don't apply any viscosity here, which is this point here, our solution will blow up. It's totally useless if you apply that scheme. And if you choose this viscosity very carefully, just on the lower multi-levels, so not on the finest grid where we want to compute the final solution on, but on the lower levels, we observe that and we get a convergence here. And this is now what we can use again in order to get more speedups for that. So we have different studies here for the IMIX methods and for the Semi-Lagrangian set-TLS methods on the lower grids here. And for the IMIX method itself, we get the biggest speedup here for the IMIX method here for a 2-level method and a filtering approach here. So this is speedups here. This is the error itself. And if you have a set-TLS method itself, it's limited here in the errors here because we have an interpolation in it. So it's always limited here in the errors here. That's the interpolation error in space. Once you use Semi-Lagrangian methods, you always get this limit here. But we observe that we get a pretty good speed up here if you use 3 levels and a filtering method here. And if this point would be sufficient with respect to these errors here, then we would even be able to talk about a speed up of 10. Again, please take that under the careful statement here from my side that this has to be analyzed further. So this doesn't say that we now get a proper speed up of 10, but this is really just about showing these error plots here. And further physical studies have to be done, like about physical properties of these equations. Okay, saying that, I'd like to wrap up that presentation here. So we have, on the one hand, this REXI formulation itself, where we can approximate the linear operator with rational approximations. Be warned about that Helmholtz problem. It's the bad Helmholtz problem. These problems which no one likes to solve and which no one can solve efficiently with iterative solvers. There are ways to take arbitrary long time subsizes. So it's not limited by the CFL condition anymore if you have a linear operator. And the results showed that instead of using a quite cumbersome exponential integration for the linear parts, maybe just using a higher order Runge-Kutta method could be an alternative, at least for atmospheric simulations here. I also showed you the parallel STC version here, where I showed you how we can infer the STC version, first of all, from the Picard form, and then we can apply a precondition of that, and also showed the first results which really show that we can gain speedups for that. And I like to emphasize here is, what I like to emphasize is once you implemented an STC method in your scheme, getting that parallel STC running is almost for free. For the FAST method itself, I'll show you results which were Pareto optimal compared to the STC methods themselves, so compared to the parallel time method. But one of the big challenges also in our community was to get this running without viscosity. So we had to apply viscosity on all the levels. And now with MGRIT, so we switched first of all to the MGRIT approach to just take all the Lagrangian methods in here. And then if you apply a very carefully chosen filtering method only on the lower levels, only on the coarser levels, we get a convergence, we get significant speedups, and we can even get a convergence with more than 2 levels, which was also one of the big challenges. But now I'd like to hand over again to Georg by saying, yeah, first of all, thanks for your attention, and I'm ready for any questions.
Thank you for the nice talk. So I have a question about you have considered smooth problems without orography in the bottom. So have you tried to apply this for steep topography in the bottom? What happens then?
We applied that also to topography. So we had some benchmarks which includes that without significant changes, but I never applied it to steep topography. So also for the shallow vault equations, we never did that. So these are studies which have to be done. But thanks a lot for pointing out that additional challenge, which we definitely do in the future.
Thank you.
So from a layman's perspective, because I'm not an expert in climate simulations, what is the problem with adding viscosity?
Adding viscosity should only be done as a last step. Like if you put the physics into that, so viscosity is part of saying, well, we know that there's a certain viscosity in our atmosphere. But to develop numerical methods, it's considered to be very, very bad practice that you have to add viscosity to your scheme, because it just introduced something to your numerics which damps out certain modes which should not be damped. So it's all about the damping of modes. So it's our highest art to develop methods which do not need any artificial viscosity in it. And then later on, viscosity should be added as the physics. So this is how all these developments are working. And basically all of these models, let it be ECMWF, let it be the Met Office, a lot of work has been put in that no artificial viscosity was necessary to be added as part of just in pure numerics around that to solve the order equations.
I have another one. You showed a lot of data on convergence versus time to solution, but what about the scalability, the actual scalability of the code? So is that a challenge with these parallel time methods?
If you think about climate simulations, we know that they'll run with a very, very low resolution, and the scalability stops after a few nodes if you use a very low resolution. And then again, the challenge is, how can you scale that up further? For the weather simulations themselves, you can scale them up pretty well. There have been some studies, but it's getting, again, relatively expensive to run them. So there's again and again a crossover point when parallel time methods show that they provide benefits because of the lack of scalability for these models. But in the end, it's always a matter of how much workload you put on the supercomputer. So if you use an extremely high resolution model, it scales definitely in a very good way, but it also takes a very long time to get the solution because of the CFL condition. You have to take smaller and smaller time sizes. So it's not only a matter of scalability, but it's also about saying if you increase your resolution to make it scale better, you also have to have a considerable increase of the entire workload you have to solve per node.
Is there something similar also for nonlinear problems? Parallel time?
So everything you saw here included nonlinearities. But there's no rational approximation for these nonlinearities. But I can tell you that what machine learning currently tries to apply is actually approximating something similar. So I try to approximate that exponential landscape, like on the complex plane. And what machine learning is doing is basically the same, approximating the manifold for the nonlinearities. And the rest, what you saw about the convergence, about Semi-Lagrangian methods, this is all including nonlinearities. I hope that's what it meant with nonlinearities.
Yeah, thank you.
I have a comment about what you said about Louis Fry Richardson. I'm also a big fan of his, and actually, not only did he invent parallel computing using human computers on a spherical like domain that's supposed to map the Earth. He also tried to do it by hand by himself, if I'm not mistaken, during World War I while he was a medic. And yeah, that famously failed, but he was the first one to actually try it.
Yeah. So even there were some wrong calculations in it, but even if the calculations would have been right, it would not have not worked. He used I think a forward Euler method, which is inherently unstable, and so it would have never worked. So if you like to see Lewis Fry Richardson's book, I can just invite you to our next partial differential equations on the sphere conference. It's in Brazil, in Sao Paulo, and we have his book, one of his original books, which we hand over as a souvenir again from conference to conference. So I introduced that this year, and yeah, it's handed over every year. And you find all his thoughts in this beautiful book.